Welcome back. So now we did all the prerequisite work and we're finally ready to do the renormalization of QED. And the first step, just like we did with lambda phi 4, is to work on the power counting and figuring out which are the counterterms, how I want to define the counterterms for QED. So in a previous video, I think video 12, we did show these, right? We were doing the general superficial divergence for any theory, right? And we saw that in the case of QED, when I only have one interaction in these two fields, right? A fermionic field, which here stands for the electron, and a photon, right? We have these numbers characterizing the QED interaction. So there's the two fermions in the vertex. There's one photon, no derivatives, right? This is related to the spin of these two particles. And then you see that the delta for QED in 4 dimensions, right? If I plug all these numbers here for 4 dimensions, you see that delta for QED is 0, which means that QED is renormalizable in 4 dimensions. Right? And that is an important piece of information. We also saw in that same lecture that in general, right, the superficial degree of divergence for any theory can be given by this expression right here, where you're summing over all the interactions in your model and you're summing here over the fields that you have. Right? So now we're working in 4 dimensions, so I can substitute these one for 4, right? Here I'll have 4 minus 2 over 2, which is 1, right? This will be just 1. And since QED only has one interaction and delta for that interaction is 0, right? This whole term goes away. So you see that QED in 4 dimensions is kind of special, because the superficial degree of divergence does not depend on the number of vertices, right? Just on these number of external legs for the diagram, right? And this is easy now to calculate, right? You just have to plug in these two fermions, two fields here, right? And so this is 4 minus, in the case of the fermionic field, this is half. So we have 3 halves here, right, because of this plus 1, over the number of external electrons, let's call it like that. It's easier to remember than n psi, right? And in the case of the photons, right, this is 0, so it's just minus 1, right, times the number of photons, which I'll indicate like that. So you see, this is the expression I wanted. And it's a very useful one in determining how divergent a diagram is, because all I have to do is now worry about increasing the number of external legs. And also, I mean, unexpected, since the theory is renormalizable, you can see that eventually if I go to more and more complicated diagrams with more and more external legs, eventually D becomes negative. And then all of those diagrams are convergent. So I only really have a finite number of diverging 1pi functions, and those are given by the simplest things, right? The ones with a small number of external legs. So now what we need to do, right, is do a classification. Let's look, starting from the simplest case with no external legs, and put more and more legs until we found all of the 1pi functions that are actually divergent. So the simplest case is just this, right? I'll call this diagram A, right? And this is just all the sum of all the 1pi diagrams with no external legs. The superficial divergence for this guy is, of course, 4, because I have no external legs here, but which makes it highly divergent. But I don't actually have to worry about this guy, right? We have proven in quantum field theory 1 that these are just vacuum bubbles right, that are exponentiated and eliminated from any observable. So I won't be able to relate that to any physical observable that I could use even to renormalize those diagrams. So they are not physical, they don't influence physical measurements, so I don't have to worry about them. The second class of diagrams, let's call this B, is when I take this guy and add now one external legs. Let's start adding photons first, right? I could start by increasing photons or electrons. Let's start with that, right? Increasing a photon, according to the formula, this formula decreases the superficial divergence by 1. So the superficial divergence of these guys is 3, right? Let's continue our classification. Then I can take this guy, let's call this class of diagrams C, right? And put yet another photon. So now I have something like that, right? Which we called self-energy. In this case, is the self-energy of the photon. Right? Again, increasing external photon leg lowers the superficial divergence by 1. So now D is equal to 2, also divergent, right? Again, one more leg. Let's call this D. Right? Now I can go and think of a 3-photon vertex. Like that, to look better. Right? 3-photon vertex, which has D equal 1. Again, because I'm increasing the number of photon legs. Let me copy this because soon won't be able to see it. Paste it down here. And then we can increase yet another photon leg. Call this one E. And that's what it looks like. Right? For this, D is equal to 0. So at least superficially, this is the divergent as a log, right? And then, of course, if I put one extra photon leg, then I have a convergent diagram. So I don't have to go any further in terms of increasing the number of photons, right? So I'll do the opposite, right? I'll now increase the number of fermions. Let's call this class of diagrams F, right? And as we know, because of charge conservation or the conservation of number of fermions, I have to add fermions in pairs, right? If I have one fermion going in, I have to have one going out, right? And this direction is arbitrary, right? So putting two legs, two fermionic legs, right? I put NAE equal to 2 here. So I have a -3 in total. The divergence here is 1, right? Which also makes clear that if I try to add now 2 more external fermions, right? I'll subtract 3 again, and this will be a -2. So I don't have to put more fermionic legs. Otherwise, it will be convergent. But I can put an extra photon, right? I could take this guy right here, right? Let me do this. Call this diagram G. And put the same here, 2 fermions. But 1 photon. 2 fermions and 1 photon. That way I have 3 here from this piece and 1 here. That's superficially divergent, again, as a log, right? And again, if I try to increase more photons here or more fermions here, I'll have only convergent diagrams, which shows how powerful this kind of analysis is, because I pretty much just classified all potentially divergent diagrams in QED just by looking at this nice formula right here, right? Which is pretty useful. Now, that's the point where symmetries kick in, right? In principle, those guys are all divergent, right? But this guy I already said I don't have to worry about. I'm already forgetting about this guy, right? but all the other ones in principle are important, right? But let's see what symmetry does to those guys. The first diagram I want to look at is this guy right here, the so-called tadpole diagram for QED. Right? And the important thing to remember here is that while I'm drawing all these external photon legs, I'm really talking about the amputated 1pi diagrams. So the photon propagator is not really there. But I know that before amputation, this photon, right, was connected to a QED vertex inside the diagram, right, which has this form, right? I know that at that vertex, I have a current acting on the vertex. This is the wrong color, which is given by psi bar gamma mu psi. So that photon propagator was contracted with this thing. So in practice, what I'm calculating when I'm looking at that diagram is really something that is a complicated sum of diagrams, but in each one of the diagrams contributing to that sum, I have something that is like two fermion lines, right, that connect to the rest of the diagram, connected to this vertex that carries this index gamma mu here. So I have a mu here. There's some momenta going inserted by this current, and then no other external legs because I amputated this leg right here, right? So that 1pi function is proportional to this, right? It's proportional is given by this Fourier transform, right? Because I'm in the momentum space. This is the momentum going at that vertex. X is, I'm just assigning X to the position of the vertex, right? And since there's no external legs, I'm calculating the vacuum expectation value of this operator that's still acting on that vertex, right? This is what I'm calculating by what I mean by calculating this diagram B. I don't have to worry about the propagator, right? So when I do that, it should be clear that this needs to be zero, or at least for those of you that ever heard of spontaneous symmetry breaking, because this is a Lorentz vector, and if I find an operator that has a non-zero vacuum expectation value, right, that means I'm spontaneously breaking Lorentz invariance. Suddenly I have a direction, right? If this J, if there's a number J mu which is different from zero, I just choose a direction in vacuum which is preferential in some way, and that's not acceptable in the vacuum, right? That could be acceptable in a material, right, but not in the vacuum. We have never seen Lorentz violation in empty space, right? So that's one reason why this is zero. But if you never heard of spontaneous symmetry breaking, there's still another reason, which is that QED respects charge conjugation, right? And that means that this is the charge conjugation operator, right? The vacuum of QED is invariant under charge conjugation, right? And we have seen in quantum field theory 1 that this operator, the current, right, transforms under charge conjugation in this way. So it's odd under charge conjugation, right? That means that if I apply these charge conjugation operators and insert it here and here, right, I'll prove that these right, I'll just insert CC dagger here and here, right? The vacuum won't change, but this part will change sign. So this will be minus the same thing, which proves that this is zero. So what I'm seeing here, that is both, there are two symmetries, right? One is Lorentz invariance, And the other one is invariance under charge conjugation. Both demand that this guy is 0. So let me go up here. And what I'm saying is that I don't have to worry about this guy just by symmetry considerations, right? Should be also clear that this also applies to this guy. In fact, any diagram with an odd number of external photons will be also proportional to something similar. In the case of 3 external legs, I could generalize these arguments I made here. Now I'll have like 3 insertions of these current operator with, I don't know, some other index nu and alpha, right? And this will be something proportional to the vacuum expectation value of now 3 currents. I won't put all the indexes here because it's not needed, right? And then if you do the same charge conjugation argument and insert them all over here, you still have something like -1 to the n, when n is the number of external legs, in this case 3, right? Times the same thing. And again, every time this is odd, I need that diagram to be 0. So that also allows me to conclude that I don't have to worry about this guy right here. So all 1pi functions with an odd number of external photons are 0 by symmetry. Of course, that does not apply to this guy down here, because despite having only 1 external photon, it also has these external fermions, which change the analysis, right? And that means that this is all the diagrams which are really not important. We'll have to spend a little more time in the other ones, right? It's always good when everything is 0, but that's not the case for these other 4 guys. So let's start by looking at this guy right here, right? Now we have to do a more careful analysis for the other 4 classes of diagrams, and we start with the electron self-energy, which is this 1pi sum right here, right? Let's define this, right? So I'm using now definitions that I'll be consistently using through the rest of the course. So this guy I'll baptize as -I times sigma of p slash, right? So this sigma is essentially this sum of 1pi diagrams, and I choose to give it a factor of -I. This is consistent with most books, but it's the notation from Pesky, right? And what I want to do with this guy is the same thing that we did back when we were looking at the divergences in lambda phi 4. As you might remember, we did a Taylor series in powers of momentum, because going to higher derivatives of this function regularizes it. So the divergences are on the first coefficients of this Taylor series. So I want to write something along the lines of these. Of course, in this case, it's a function of p slash, so it will be a power series of p slash, right? So then you have p slash times p slash, which is p squared, and so on and so forth. And these coefficients are defined by this derivative in respect to p slash of this 1pi function, right, close to p slash going to 0, right? So I'm doing essentially a Taylor series for this diagram. Here there is a caveat, right? We know that this guy will have a higher superficial divergence than this one, than this one, just because I'm putting more powers of momentum in the denominator. And so we could say that eventually these guys will become convergent. But that applies exclusively to the ultraviolet divergences, right? So far in the course, we have focused almost exclusively on what these divergences that show up when you go to high momentum in the loop. But now that we're dealing with QED, there's a massless particle in your theory, the photon, right? And when you have massless particles, there's another kind of divergence. So just to be more concrete, the very first contribution to this 1pi function will be something that looks like that, right? So that's an electron going in, and there's a photon here. And this loop has problems also when the photon is too soft, right? If you put momentum really close to zero for the photon here, since the photon is massless, there will be another kind of divergence, which we called infrared divergence, right? For now, I don't want to worry about those. We'll have to deal with these divergences once we start really calculating these. We'll calculate these at one loop, right? All these coefficients. And then we'll have to deal with these divergence. But it's completely different in nature from the UV divergence. And so for now, when I say these guys will eventually be convergent, I mean UV convergent. They all can be potentially infrared divergent, and we'll deal with that later, right? So keep that in mind. So far, I just want to mention this because some people might have heard about infrared divergences and might be wondering, oh, these guys are not really finite at all, even if I go down this series. So keep in mind what I'm saying, they are convergent, I mean UV convergent. I will analyze how they behave in the infrared later, right? So with that in mind, in here, since I'm doing derivatives in p slash instead of p square, right? Each derivative, right, when I take a derivative like that, right, it will act inside the diagram in some loop, right? It will find a place where I have a loop. Of course, p slash p, momentum p is this external momentum that is going into the diagram here or there. I don't know why I'm drawing from right to left in this case, but it's fine, right? And it will eventually pass inside some loop, right? This derivative acting on p slash will find a term that looks like k slash plus p slash minus m, where m here is the momentum of the electron, the mass of the electron, sorry, right? And this will become minus 1 over k slash plus p slash minus m squared, right? So you see that now I'm increasing powers of momentum in the denominator, but it's just one at a time. So if whatever is the divergence, the superficial divergence of this guy will have these d minus 1, d minus 2, and so on and so forth. In the case of lambda phi 4, they decrease by 2 every time. In here, they decrease by 1, right? So in principle, right, as we did the analysis of this diagram and concluded up here that the superficial divergence for the whole thing is 1, right? That means that naively, this guy would be superficially divergent as a linear function of the cutoff, right? Lambda. This one will be logarithmically divergent, and then the rest of them are finite. Again, UV finite, right? But now, again, symmetry kicks in, right? In this case, is a symmetry that we also mentioned in quantum field theory 1, right? Which is the chiral symmetry, right? Let's try to quickly remember what it is all about, right? So we can rewrite these fermions, which are Dirac fermions, in terms of a left-handed piece plus a right-handed piece, right? And then if you look at the mass term for this, let me call the mass m0, because now I want to be careful about unrenormalized and physical, I mean bare mass or physical mass, right? If I look at the Lagrangian, I'll have a term like this, the bare mass times psi bar psi, right? But then if I substitute these, right, the projection of left-handed and right-handed operators is such that this term will be equal to psi bar left psi r plus psi bar r psi left, right? This is a very special form because if I take the bare mass m0 to be 0, right, the kinetic term for these guys that looks like psi bar gamma mu psi, right? There's a derivative here contracted with psi bar, but I don't care. I'm looking only at the Dirac structure. This can be written as psi bar L gamma mu psi L plus psi bar R gamma mu psi R. This is true both for the kinetic term and the interaction in QED, right? That's the same form for both. In one of them I have del slash, and the other one I have a mu a slash, right? In fact, a slash. But it's the same form. That means that the only term that actually mixes the left-handed field with the right-handed field is the mass term. If I take this to be 0, then I have two separate theories. I have a theory for left-handed fermions and another theory for right-handed fermions, right? And there's no way these two independent theories will produce a mass term that mixes these two fields. They just have become two really independent theories. And that means that if I do that renormalization, where I define the physical mass as some m0 plus delta m pictorially, right? I can still have powers of z here and there, but if m0 is 0, right? The physical mass needs to be 0 too, because there's no way I'll mix these two guys, and there's only a mass for Dirac fermions if you have a mixing of these two fields. And that means that delta m also needs to go to 0 as m0 goes to 0. These two things need to be proportional, right? And that means that by dimensional analysis, right, this is the guy that these coefficients here will be the guys that introduce delta m. Remember, when I put renormalization conditions, delta m will be proportional to the loop contribution, right? If delta m needs to be proportional to m0, right, that means that this guy right here needs the part that is independent of momentum, right? You see that here I have two divergences. One that is proportional to momentum, and we know that this will be the one that contributes to delta z, right? If you don't remember this, go back to the lambda phi 4 case. That will be more obvious there, right? We'll show later for QED. And the part that is independent of momentum is the part that contributes to delta m. So this part needs to be proportional to m0, right? Times some other coefficient, let's call little a0, and then a cutoff. But I cannot now put something linear in the cutoff because this has the wrong dimension, right? This guy has dimension of mass. So at most, this can be proportional to the log of lambda, which is adimensional. Of course, there's some other number that goes here, right, as we have seen. But by dimensional analysis, and this demand that comes from chiral symmetry, you can see that the divergence must be softer, let's call it like that, than linear in lambda. It must be at most a log of lambda. And of course, there is this part that will be just given by some a1 p slash log of lambda, because here there's no constraints, and the rest is finite, right? So there's also finite terms, right? So again, we see an example, and I mentioned this before, right? I said, well, these coefficients, right? What I'm seeing here is that you have a divergence proportional to some cutoff, right? But in general, you could take that A0, right, and write it like this, right? I have some A0 lambda plus A01 lambda 1, A02 log of lambda, right? And symmetry could make some of these coefficients be 0. And that's what's happening here, right? In fact, we will calculate, again, this is not something you need to impose. Symmetry is just allowing us to see this without doing the calculation. But we'll see once we calculate this guy, right? Of course, we cannot do the whole series, and that's the advantage of symmetry. It's telling us something about the whole sum. But at least at one loop, we'll calculate this explicitly, and without imposing any symmetry, these will come out naturally, right? Because the theory has this information about the symmetry. So our analysis is telling us that this electron self-energy will contribute to independent divergent coefficients here that will lead to different renormalization conditions. Now, the next guy we want to look at, let me go up, is this guy right here. So we have already seen that the superficial divergence for the whole thing is 0, right? And now I want to define, again, I'm also using this opportunity to define, give names to all these quantities, right? So this, I'll name minus I E, as I have talked before. I am always putting explicitly a charge here, and I'll call this guy gamma mu, and depends only on two momenta, which we usually choose as the fermion ones, which I'll call P and P prime here, right? I can do the same trick I did for this guy, just take derivatives in one of these momenta here, right? But we see, since we starting already from d equals 0, right? Only the very first term will be important, right? So these will be, you have some matrix here, maybe you can call this A mu, right? A mu is already used for the photon, I don't know, A0 mu, right? Times a log of lambda, which is the equals 0 part, right? The logarithmic divergence plus finite terms. And that's pretty much it. There's no symmetry tricks that we can use here. And remember that this is some combination of Dirac matrices, right? There's a Dirac structure here too. This guy has two Dirac indexes, right? IJ, which need to appear here too. So this is really a matrix in spinor space, right? So that's okay. That's another divergent coefficient, right? So another divergence that is independent of those two. So in total, I have 3 so far, right? Now, the next thing I want to look at is the photon self-energy, right? Which, pay attention here, right, is starting from d equal 2, right? So keep that in mind. In principle, is diverging like the square of the cutoff. But let's see what happens once I apply some symmetry considerations. I'll call the momentum going here Q. And of course, this guy carries some Lorentz indexes. Let's call them mu and nu, right? Which are contracted to this external photon legs here. So again, I'll be defining this guy in this way. This will be just an I times, I'll call the self-energy pi mu nu of Q. So this is the photon self-energy. And you see that this again is mapping nicely to what you would expect to be important so far, right? One is the correction for the electron propagator, the other one is the correction for the photon propagator, and this one is the correction for the QED vertex, right? Fine. So now this guy, quite generally, right, since he has two Lorentz indexes, right, the most general, and depends only on one momentum, right, the most general thing I could possibly write is this, right, some function, let's call pi a of q squared times g mu nu plus some other arbitrary, right, an independent function of q squared times q mu q nu, right? This is the most general thing I can write since I need a Lorentz tensor, right, of rank 2. And that's the only Lorentz vector I have at my disposition here, right? So I have a scalar coefficient times g mu nu plus another scalar in the sense of Lorentz scalar, right? Coefficient times q mu q nu, right? But now I can use word identities. So one of the exercises I gave you on the previous video, right, was to prove that this is 0. Right? If I contract, this is very similar to the word identities, but I don't need this photon to be on shell. If I just contract here, instead of the photon polarization or the photon propagator, I contract the momentum of the photon, right? This needs to be 0 by word identities, which are the quantum manifestation of the U1 symmetry of QED, right? In order to satisfy that, right, let's see what happens, right? If I do contract this with this generic form I wrote here, what happens, right? So Q mu pi mu nu needs to be 0, but on the right side here, this will become pi a of q squared, and then q mu contracts with g mu nu and becomes q nu, right? And here q mu will contract with this other q mu right here, and we get pi b of q squared times q squared q nu, right? And this needs to be equal to 0 for any value of q, right? Which means now that pi a q squared, right? I am eliminating q nu here because this needs to be true for any value of it, right? I throw pi a to the other side and this becomes minus pi b q squared times q squared. So you see this tells us that these two things that could be independent in principle, right, for general tensor, right, cannot because these won't satisfy word identities. So there's a relation between them. I'll just baptize these. I just give names to these functions. I'll call these pi of q squared times q squared, right? So I'm really defining this guy to be minus pi b, right? And then if I substitute that up there, right, I just exchange pi a q squared by this and this guy by this, right, I get just a constrained form, let's say, for pi mu nu, which is the most general one allowed for QED, right, which has this symmetry, right, implemented by the word identities here. G mu nu minus q mu q nu pi q squared. So what I'm saying is that instead of this form, I'm constrained to this one, which is it's more constrained, right, and satisfies word identities. Now, if you look at this, you see this is already our Taylor series, right? I'm already expanding this function in powers of q, right? And if I'm showing that this is the most general form possible, right, I'm already starting my series from q squared, right? What I'm saying here is it is impossible to have anything independent of q or linear in q in my Taylor series. Those two first coefficients, which I would call a0 plus a1 q nu, are 0. I'm starting from a2, which is proportional to k nu or q squared, right? Both are here, q squared and q mu, q nu. So that d equals 2 that I started, right? From symmetry considerations, I'm seeing that that would be associated with the a0, that's 0. D equal 1, that would be associated with a1, is also 0. So the surviving terms have d equals 0, which are proportional to a2 times 2 powers of momentum. Again, symmetry is lowering the degree of divergence. And that tells me that this guy, which is essentially a2, right? This guy is essentially a2 plus or some factors in front, right, is logarithmically divergent. So what I'm seeing is that pi q squared is proportional to the log of lambda, right, plus finite terms, right, which is pretty important because I can always rewrite the self energy of the photon in terms of this function, and this function has only one divergence, right? I could even put an a0 here if you want, but it doesn't matter, right? It's one more divergence and one more condition. So you see here that we had two examples, right? One coming from the gauge invariance of QED, more specifically from the local version of it, but implemented to word identities, and another one coming from chiral symmetry, right? Where we see that and again, these are contributions, these are self-energies, so in principle they could change masses, right? And we see that these masses, both the mass of the photon and the mass of the electron, are protected somehow from corrections, highly divergent corrections, due to the loops. And they are protected through symmetries. We see the protection in the case of the photon is even stronger than in the case of the electron, right? But we'll get to that, right? But the important thing is to have that in mind. In the case of the electron, it's even more striking in a way because that symmetry is really broken, right? What I'm saying here is that when the chiral symmetry is broken, and that means M0 is different from 0 and these two guys are mixing, still I have some constraint coming from the symmetry, because the correction needs to be proportional to the explicit breaking parameter, which in this case is m0, right? So even when the symmetry is not there, it still serves as a guideline or as a constraint to what can happen or cannot happen, because you can still think of the limit where this symmetry is restored, and that's a pretty powerful tool, right? Now we're only missing one guy, right? Let me go up real quick, right? So we dealt with this self-energy, there's two divergences here. This one, there's only one. We dealt with this one, there's another one, so 2, 3, 4 divergences. And now there's this guy. Let's think about this guy a little bit. So we're starting from d equals 0 already. And now, of course, this guy will also be subject to word identities, right? In particular, we know that we can contract, right? This has 4 different photon momenta here. I call K1, K2, K3. The direction does not matter too much. K4 here, right? And the point is that word identities tell us that whatever Ki going 1 to 4, I contract with this guy, it needs to be 0. I can exchange any one of those legs and contract by the momentum going into the leg with the rest of the diagram, and that needs to be 0, right? Coming from the word identity again, right? I won't show it here, but that also constrains the most general form of this guy, which is now something with 4 Lorentz indexes, right? To have a particular form, right? Which will be something that looks like that. G mu K1 sigma minus G mu sigma K1 mu contracted with something similar for K2, so G some indexes K2 minus G some other combinations of index K2, and the same for K3 and K4. Let me change the... And this is the most general form that this guy can take, right? Again, it's very similar to what we did for the 2-point function right here. Right? Even the form is somewhat similar, right? But then you see there's already 1, 2, 3, 4 powers of momentum here, and I was starting from a superficial divergence which is 0. So I'm going way down the Taylor series already, right? And that means that the very first term, with which is different from 0, will have a d equals -4, right? So this diagram is convergent, and it's just finite. All the sum of 1pi diagrams here is finite. Again, you could potentially, just by doing this analysis, right, have a logarithmically diverging 1pi function, but you don't because of symmetry. Makes all the first coefficients to be 0, and that kills the divergence in this case. And this is the summary of our discussion so far, right? So I have these 3 divergent diagrams or 1pi functions, but they have just 4, right? 1, 2, 3, 4 independent diverging quantities, right? So I'll need to eliminate these 4 divergences to do the equivalent of 4 redefinitions, right? Or renormalization conditions, right? Now you can stop a little bit and think about it in analogy to what we did to lambda phi 4, right? There we had just one field and one coupling, right? And that means we had potentially 3 conditions, right? One that redefines the coupling, and 2 that redefine the position and the residue of the propagator for that one field we had. So we had potentially 3 conditions. In QED, we have 2 fields and 1 coupling, right? So there's a condition that comes from physically defining that coupling. And in principle, you could have another 4, right, for the position of the pole and the residue of each of the other 2 propagators. So the position of the electron pole, which is the mass of the electron, the residue for that pole, the position for the mass of the photon, right, and the residue of that pole. So in principle, you could have 5 conditions, physical definitions, and you only have 4 divergences, right? But there's one more consequence of this form right here that we didn't explore yet. So let's take a look what happens to the full photon propagator once I accept, right, that in order to satisfy world identities, I need to have this form for the self-energy. So let's take a look at this object right here. So now this empty bubble here means all connected diagrams, not just the one pi diagrams, right? And the only inclusion besides the one pi diagrams is really the free photon propagator and interactions, of these same diagram again and again. Right? So I have this guy, but then I also have something like this. Let me see if I can get this. And so on, right? So now for the full photon propagator, I have the free photon and the free photon propagator, and also these repeating pattern of one pi diagrams, right? If I write an expression for this, and here I will be using Feynman's gauge, in which the photon propagator is the simplest, just to save us from big calculations, right? The free photon propagator is just minus I g mu nu over q squared, right? This next diagram will be given by, let me do it like that. The free photon propagator times this 1 pi function, which is defined right here. Let me write it. Of course, the Lorentz indexes must be contracted, so let me change this nu to rho, right? And in here you have Q2 G rho sigma, because this rho needs to be contracted to that one. Q rho Q sigma. This function, pi of Q2 times, let me put a bigger bracket here to avoid confusion, times again this guy, but I need to fix the Lorentz indexes. This needs to be sigma nu, because the whole thing is mu nu, right? I'm using the same convention I used here. So the full propagator should have indexes mu nu, right? And so on. I won't repeat the next one, right? Will be even more complicated version of this. So I have this 1 pi function again, right? Now it's important to notice that this piece here can be rewritten in a convenient way. So I can take this thing here. So Q2 G rho sigma. I'm talking about this whole piece, right? You can take this Q square inside, right? there'll be a cancellation with this Q square here. So this becomes just G rho sigma G sigma nu minus, and then now I have a Q square under these guys, Q rho, and this Q becomes Q nu because I'm contracting with G sigma nu over Q square, right? Times pi of Q square, which I can now write as delta rho nu, right? Because of this contraction, minus Q rho Q nu over Q square. Again, times P mu nu. And I want to call this, all of this is applied to pi, right? And I want to call this thing in parentheses here delta rho nu. And what's important to us is that this guy satisfies this important property, which is that delta mu nu times delta nu beta is just delta mu beta. So this guy is square is equal to itself, right? And that can be checked. You just contract these with itself and you see you get the same expression again, right? It's quite easy to show. And that means that the whole series becomes suddenly quite simple, right? That means that that series up there, once you have this property, this thing becomes equal to this, I'll just repeat, right? Then this guy times delta rho nu of pi Q square minus, again, this guy just repeats, I G mu rho over Q square. Again, now I think I can remove this, just make it clearer, right? Then I'll have two deltas, right? Delta rho sigma delta sigma nu, and then I have P pi Q square twice, right? I can rewrite the whole series as powers in delta, but since delta satisfies this property, this will become, right, just this guy that's just repeating, this one times this delta rho sigma, but again here I have delta rho sigma, and that will be true for every order. So this delta just factors in front of everything, and I end up with a power series in pi. It will be this plus pi square plus pi cubed, right? It simplifies a lot because this operator is idempotent, right? It comes out of the series. And of course, this is just a geometric series, right? Which I can rewrite, right? That's the same trick I used to show that the self-energy for the lambda phi 4 field changed the mass of the field. But now it's a simpler power series, right? A simpler geometric series. This becomes, let me just copy everything. Now I want to rewrite this delta explicitly. Let me color it. So I'll write it explicitly here, delta rho nu minus Q rho Q nu over Q square, right? So this is just a copy of that. And this whole part here, I can resum, right? And this becomes, I'm missing the 1 here, so I'm subtracting 1 for the whole series, pi of Q square, minus 1 because I'm missing the first piece of the series here, right? And now I can just expand this product, right? You can see that there's a piece here which is opposite sign to that one, so there'll be a cancellation. This guy will go away, right? And you have this guy just multiplying the rest. It's a little bit of algebra, but not much. And you can see that this will become Q square 1 minus pi of Q square times the structure G mu nu, this guy, right? Minus Q mu Q nu over Q square. And now in this cancellation, there's a part that does not disappear, which is this one, minus I Q square Q mu Q nu Q square, right? To get from here to here, you just have to open everything and see that these goes away, and that's what's left, right? But now, there's also something else that we should remember. As far as S-matrix calculations go, right? This is the full photon propagator, but we will never use the full photon propagator alone, right? It will always be contracted to some bigger matrix element, right? And then we will amputate it. But in that contraction, what happens, right? What I'm talking about is this. Let me take my full propagator bubble here. This guy will appear somewhere like this, right? This will be a photon propagator. This is the full thing. And then it goes into some bigger diagram with a number of external legs, photon or fermions, doesn't matter, right? Could have both. And this is the guy we're looking at. It has indexes mu, right? But when it contracts to that, right, what we're talking here is that we get this expression. What we're saying is that you have this expression, and nu will be contracted with the rest of the diagram. Now this is the part for the propagator, and the rest of the diagram, this guy here, I could just write as m nu of q, right? Again, I'm doing that separation where I have the full propagator here and the rest of the diagram. But we know that q nu m nu is 0. So there's a lot of structure in this propagator. I missed a parenthesis here. There's a lot of structure in this propagator that never contributes to any matrix element, right? So I can really just work with the full propagator. That is this. This is what will be amputated. Really, the only thing that I need to amputate to get a S matrix element, right? So when I'm talking about putting the external photon on shell to get a S matrix element, this is the thing that will produce the pole that gives me a on-shell photon. Right? For all purposes, this is the full photon propagator. So now that's very important. It has a different form from the lambda phi 4 full propagator, because now you have, instead of just q square minus the self-energy, you have this 1 minus the self-energy here. And this is important for the following reason, right? I have to worry about where is the pole for the photon, right? I know that when q squared go to 0, apparently I have a pole here, as long as this function does not somehow disappears with that pole, right? But the thing is, this guy, right, the self-energy of the photon will have contributions, right? The very first contribution to it will be something like that. A pair of electron-positron, right? This is the very first contribution to the 1pi sum here. And you could have more complicated things in the middle here, right? So essentially what you have contributing to these, remember we can describe these by a spectral density, right? And the contributions to the spectral density will be states of many electrons and positrons, free or bounded to each other. And we know there is no bound state in QED with mass zero. In fact, the only thing in QED that has mass zero is the photon itself, right? And the photon does not contribute to this 1pi, right? There's no such thing as this, right? The photon propagator itself is not included in the 1pi sum. Right? You can see that in the full photon propagator, this is the free photon propagator, and then the 1pi sum. This is not here, right? So by what we can say then is that this guy is regular, right? There's no poles near q squared equal to 0. It will have poles near, for instance, twice the electron mass, but not near q squared equals 0. And that means that the position of the photon pole does not move at all, right? And I'm proving this at all orders in perturbation theory. The calculation as this just did is totally non-perturbative. Right? What I'm saying here is that word identities not only tell us, right, like gauge symmetry at the level of the Lagrangian forbids a explicit mass term for the photon, but now we are also seeing that the Ward-Takahashi identities, which are the spiritual successors to gauge symmetry in the Lagrangian, right, also forbid that the photon will get a mass at higher loop orders, right? It's protecting, again, this is the protecting effect of symmetries. It's protecting the mass of the photon from getting radiative correction. So the pole stays at 0, and that gives us one less freedom in fixing renormalization conditions, right? This is already fixed from the start. I cannot choose where the pole of the photon is, right? So of those 5 conditions that I had, I'm left with 4. I still need to do a physical definition where the residue of the photon is, but not the pole. So I get 4 conditions and 4 divergences to get rid of, right? So you can see that if, even from the physical sense of the word of renormalization, I also lose this freedom, right? So the mass of the photon is fixed to 0, and I don't need to do a physical definition of it, right? You can actually also show that, suppose you break word identity. You take this guy and you pretend you don't know it needs to satisfy word identities. And you write just some ansatz for it, right, like this, which is breaking word identities. Remember, in word identities, I would also need a piece proportional to q nu. But suppose you do that, you just break it, right? Then you see that the full photon propagator, in this case, right, which is the simplest one you can see, will be proportional to this, right? And this bidimensional analysis has dimensions of mass. So you move the pole away from 0 in the direction of m squared, right? The pole goes to m squared, right? So you can see that breaking word identities, at least in this very specific case, moves the pole mass, which reinforces this interpretation I'm giving, right? Which is the mass is protected by ordered entities, right? So now we know what we need to do, right? We need 4 redefinitions, right? That will also be needed for physical reasons, right? We need to do a physical definition for the charge, the mass of the electron, which are the 2 physical quantities measurable in QED, right? The mass of the photon is fixed by symmetry, right? And then, of course, the residues. These 2 residues need to be normalized like we like them, right? There's this canonical way we like to normalize the residues. So let's now write the Lagrangian and do these redefinitions. So now this is our Lagrangian written in terms of the bare fields and the bare constants. Now I'm being careful putting 0 here for the mass of the electron and the charge, right? And we know from our analysis of the Chalen-Lyman representation that near the one particle poles, these full propagators will look like that, right? That defines for us Z2 and Z3. I'm using now different numbers because I have more than one field, right? So I'm calling the Z of the electron Z2 and the Z of the photon Z3. And that also defines, right, that one particle defines the physical mass, m here. And already I'm incorporating this discussion for the photon, so I'm not even trying to put a physical mass of the photon here, right? I know this pole will be at 0, so all that I have to deal with is the residue, right? That, in fact, from this analysis right here, we can conclude that Z3 is already calculable in terms of the 1pi, 2.1 pi contributions near Q equals 0, right? We can see Z3 right there. But for now, let's keep Z3 here, right? When we need to calculate it, this will be useful. And now we will, if we want to renormalize the theory, we will try to get rid of these z's in the full propagators. And we can do that by defining the renormalized fields, right? So I'll exchange psi for z2, the square root of z2 times a new field, which I'll call psi r. And these r's will go away pretty soon, but for now, let's keep them there. I use a little r, right? And the same for the photon. I'll just redefine a mu and exchange it for z3 to the half of a mu renormalize. So this is the new guy I'm defining with this expression, right? So I use these 2 definitions and I go back to the Lagrangian, right? Now my Lagrangian, which is partially renormalized because I didn't do anything yet with the couplings and masses, right, will become minus 1/4. There's 2 powers of a here, so I get a z3 f mu, now written in terms of ar, right? This is the square. Same here, there's 2 powers of psi, so I get z2 psi bar r I del slash minus m0 psi r. And of course, nothing comes from free, so the z's that I'm making now with these Lagrangians, there will be no z in the propagators, but the coupling now comes with some powers of z, right? There's 2 psi's here and 1 photon, so that will be a z2. There'll be a z3 to the power half. And then this interaction, sorry, this is E0, right? This is still the bare charge, psi bar, gamma mu, psi r, a r mu. So this is not our Lagrangian now with these definitions. Now I want to define the physical charge, right? E. Looking at this, right, I could in principle just take this whole thing to be the physical charge, because the interaction there, but that would leave me without a counter term for the 3-point function. So it's convenient here to define a Z1, which is similar to Z2 and Z3, but it does the loop effects for the 3-point function, the intrinsic loop corrections to the 3-point function. And that is what I'll call this. Right? This might not be immediately obvious why I need a third guy, but will soon be clear, right? And play an important role in what's to come next, right? And also the mass. I want to redefine the physical mass. Notice there's a Z2 multiplying the mass here, so I'll define my delta Z, delta M, right, which is the counter term for the mass, as Z2 M0 minus the physical mass. And here I define delta M actually, because the physical mass is already defined by the propagator up there. Right? So with that in mind, I can go back to these Lagrangians and make all the substitutions. I'll do also, to make the counter terms more explicitly, 3 other definitions. So I'll define a delta 3, a delta 2, and a delta 1. All of them will have basically the same kind of definition, right? So this guy will be just Z3 minus Z3 minus 1. This will be Z2 minus 1. This will be Z1 minus 1, right? And this, of course, just using this expression, right? This is just E0 over E, Z2, Z3 to the power half, minus 1. Now, using all of these up there, right, things get pretty simple. Let me copy this guy here, right? Let me see if I can keep, yeah, you can see, yeah. So this guy is just 1 plus delta 3. So you get a term which is just like QED plus a counter term. That's easy, right? This guy will be 1 plus delta 2. So as far as the kinetic term goes, it's again just the usual QED kinetic term for the electron plus a counter term, right? But here M0, right? Z2 M0, which is what I have in this piece, right, will be M plus delta M according to this definition. So again, I have a term which is psi bar M psi, just like in QED, plus a counter term for the mass, right, for the psi bar psi operator. Right? And same here, this guy will be EZ1, right, according to this definition, which is just E times 1 plus delta 1, right, using this. And then I have a interaction, a 3-point operator here, right, which is just like QED, but with the physical charge now, plus a counter term. And here you can see why I introduced this Z1, right? I'll have a counter term explicitly, a counter term for the 3-point function. So let's write all of these and group the operators that are just like QED plus the operators that are now our counter terms. So my Lagrangian is becoming something which the first line is very similar. Eventually I'll get rid of these renormalized indexes here. But other than that, it's just the QED you know and love, but now with physical constants here. So this is really the mass of the electron, this is really the charge, which again I'll have to define at some scale. We'll get to that next, right? And all renormalized fields. And now there's new stuff, right, coming from all the deltas here, right? So there's one that is just like this one, but with a counter term delta 3. One that's very similar to this one, psi bar r, but has two counter terms here. So the counter term that will deal with the position of the residue, and the one that deals with the value of the residue and the position of the pole, right? And finally, one delta 1e, which is the counter term to the interaction, right? And we'll deal with loop effects that appear in the 3.1 pi function, right? So that's our new Lagrangian now, right? And we want to know what the Feynman rules for this guy is. And here they are, right? So for the first line, they're the usual Feynman rules, now defined with physical quantities. So this is really the electron mass, right? And now you have these new counter terms, right? So the counter terms, all you have to do is remember that these derivatives become momenta, right? When you go to momentum space, right? So you get momentum dependent Feynman rules, right? This is for the mass. Also here for this counter term for the photon, all you have to do is that you can take this term and do an integration by parts to write it like, let me get another color to get something that looks like d for x of minus half of a mu, and the operator that appears in the middle here is minus del 2 g mu nu, right, plus del mu del nu, right? So these derivatives become these two powers of momentum, and these ones become these, right? So you can get the Feynman rule from this piece by doing that, right? And the one for the vertex is quite straightforward, right? So now, if I want to work in terms of these renormalized quantities, right, these new variables, I can write my 1pi functions using this new set of Feynman rules, right? And in that case, I redefine all those quantities I had before, but now this is really the physical charge, and in here you have contributions from the counter terms. Everything will be summed up in there. And then, of course, in here I'll have both counter term contributions and loop contributions, but I'll have some condition on these guys, right? And this condition will fix the cancellation between counter terms and the divergent part of loops, so that I get finite quantities out of the theory, right? And it is in those finite quantities that the physical behavior of the theory will be encoded. So of course I have to impose renormalization conditions here, right? Which are these, right? And again, since we counted the divergences before imposing these conditions, this is the opposite of what we did in lambda phi 4, which we were just guessing our way through it. Now we're being more systematic. So we know that we need 4 conditions to deal with those 4 divergent coefficients that we found out. So it's really obvious which the conditions are, right? You have to deal with position of the pole and value of the residue for the fermion, full fermion propagator, here, the self-energy of the electron. in the case of the self-energy of the photon, you don't even have this choice, right? I put this P0 here, which is some scale. We choose appropriately what we want to use here later. But in the case of the photon, there's not even that, right? The position of the pole is already fixed. So you're just caring about the residue. Just one condition does that. And finally, there's one that defines the charge. So I'm saying I'll choose some energy here, and at that energy, the charge is defined. Away from that energy, we'll have to calculate, right? And that will be set by the choice here, P and P0. You can take P minus P0, which is Q, right? It's the value of the momentum of the photon going into that vertex. But we'll deal with that on the next video, right? So the next step now, this is all, as you can see, I'm not doing perturbation theory yet, right? I'm just writing this whole sum of series. At least I'm not truncating that sum, right? But now, starting next video, we will actually calculate all these quantities. So it's clear that we have to calculate the self-energy of the electron, we have to calculate the self-energy of the photon, and we have to calculate the one-loop corrections to the three-point function, the vertex of QED. And that's what we start doing next video. See you then.